right, kids. Chapter 11, Stats with Glenn. Remember chapter 10 when we introduced the T-test? The T-test, as I had said earlier, is one of the tests that is very common in a practical sense. All the tests building up to that we did from chapters 6 through 9 were building up to the concept of hypothesis testing, but the T-test is a very practical test that is used all the time. So let's briefly review from chapter 10. We talked about the one sample T-test. We were comparing a sample mean representing one population with another known population mean. Then we did what's called within groups T-test, where you're comparing data from one variable with data from a second variable from the same participants. So that could be what we call pre-test, post-test data. If you're doing a nutritional regimen, for instance, you could see people's weight at time 1 versus time 2, which was the example we went with. A third, very useful kind of T-test is called the between groups T-test. And I know I've said this before, but this is one of my personal favorites. The between groups T-test. The between groups T-test essentially allows you to see if the mean representing one population is significantly different from the mean representing a second population. So our means representing two different populations significantly different from each other. This is the basic question of the between group T-test. Are means representing two different populations significantly different from each other? This is a very standard kind of question. You can ask if students who get one approach to statistics do significantly better or worse than students who get a second or a different approach to statistics. You can do a test to see if people who grow up in one part of the country, such as the North, are maybe more outgoing than a population of people from the South. You could ask a question as to whether children who are exposed to the young Einstein or the baby Einstein videos somehow learn reading earlier or more effectively than students or children who are not exposed to that. You can see if cats and dogs differ from each other. You can ask all kinds of questions with the between groups T-test. So this is a very versatile and practical kind of test. I'm actually going to use a topical example. So these are the days of coronavirus right now. And we hear a lot of people, including, for instance, our president, talking about possible medications that might be useful in treating this virus. And of course, all the drug companies around the world are scrambling to make a vaccine for this virus and also to come up with some kind of treatment. So if you are afflicted with the illness, is there any useful treatment? To this point, at this date, which is April 5th, 2020, there has not been any demonstrated effective treatment. By the time you're watching this, hopefully that ends up not being true. But imagine you're working for a drug company. Okay, so the other day they were talking about the importance of clinical trials. So imagine that you're working for a drug company, and I know that there's a drug that's out there that's been used for malaria, as an example, and some people are saying maybe that's also useful for COVID-19. Here's an example. Okay, so let's see. Imagine that you had two groups. You had a group that had the experimental drug, okay, and then you had a group that was what you might call a control condition. So you have two groups. Group that gets the experimental drug, group that gets some kind of control condition. Sometimes we'll call this a placebo. A placebo is when you get some kind of treatment, either an injection or a pill or whatever the format is, and you're not told whether it's got any ostensible or reported treatment-related effects or not. And usually in good research, the researcher actually doesn't know who's getting what. So imagine that here you are in the day of Corona working really hard trying to come up with a treatment. I'll tell you there's a lot of outcome variables that the medical professionals are looking at. The number one that I hear people talk about is temperature. I personally had 2 weeks of a fever and had a temperature that was elevated. And they're saying that that's kind of like the quickest. There's a lot of indices of coronavirus, but the quickest, most obvious measure that people are looking at is temperature. So let's just say that you did a study and you wanted to see if this experimental drug leads to a reduced, on average, temperature compared to people who are taking a control drug. That would be a classic between groups t-test. I'm going to give you some data. Okay, so for the experimental drug, we'll call this X1. I'm going to give you the temperature. So imagine that you administer the drug to people for 3 days, and then you take their temperature after that 3rd day, is how you design it. And let's say, I'm going to stack the deck a little bit. Let's say this person has 98, this person has 97. I'm going to put this 3rd person at 99. Okay, so for the experimental condition, the data in terms of temperature in Fahrenheit, after 3 days of taking the drug, 98, 97, and 99. For the control condition, I'm intentionally, by the way, using very small data. As I've done throughout the semester, throughout these videos, I'm using small data, or small n, for calculation-based purposes. Since we're going to calculate this stuff by hand, I'm not going to give you the number of data points that you would really want. If you were really working for a pharmaceutical company and we're doing this study, would you want 3 people in your experimental condition? No, you maybe would want more like 300 people in your experimental condition, as an example. But realize that, but realize also for calculation purposes, we're going to use small n's. For the control condition, I'm going to give you only 2 people. First person has 101. By the way, that was about my average running temperature for 2 straight weeks with this terrible virus. The second person, I'm going to put at 99. Okay, there's a reason I'm giving you only 2 people. I want to partly, again, use relatively small numbers because we're going to have a lot of calculations, as you're going to see. The calculations are pretty intense for the between groups t-test. I am also intentionally using what I'm calling unequal n's. So n1 equals 3. There are 3 people in group number 1. And n2 equals 2. There are only 2 people in the control group. The reason that I'm intentionally using unequal n's is because I want you to realize that the between groups t-test is designed to take unequal n's into account. Sometimes students, when they design a study, don't realize that. And they're like, oh, if I have 20 participants in group 1, I have to get exactly 20 participants in group 2. In fact, the way that this thing is computed, it doesn't care. You could have 20 people in group 1 and you could have 200 people in group 2. That wouldn't be the smartest design for various reasons, but the t-test does not care and it corrects for differential n's. And because of that, we're going to start with an example with differential n's. Okay. So here's the steps. Step number 1, as always, has to do with the research hypothesis and the null hypothesis. So it's the same basic steps that we've been using all along. I'm going to put mu sub 1 as corresponding to people who get the experimental drug. And I'm going to put mu sub 2 as the control condition. People who get a placebo, who get no drug. This is a little different than something we had done before. In the past, we had looked at the special population as a subset of the general population. Now that we're in the world of the between groups t-test, we're no longer doing that. We're now comparing different population means with one another. Mu sub 1 is not a subset of mu sub 2. Okay, so again, when I said this is a more realistic or more practical kind of test, this is why. The experimental drug, temperature, mean, mu sub 1. The control drug, temperature, mean is mu sub 2. I did not leave myself a lot of room for the research hypothesis. I'm going to give myself a little more room. The research hypothesis is that mu sub 1 is predicted to be less than mu sub 2. Right? If this drug is effective, then that means that the temperature for group number 2, the control group, should be higher than the temperature for group number 1. If it really reduces temperature, which would be a ubiquitous measure of reducing the symptoms of COVID-19 generally, then mu sub 1 is predicted to be less than mu sub 2. The null hypothesis, remember, is your opposite of your research hypothesis, and it includes an equal sign, so that is mu sub 1 is greater than or equal to mu sub 2. So these steps should feel very familiar to you at this point. And that's what we got for step number 1, the hypotheses. Step number 2 is kind of a doozy. Step number 2 is the comparison distribution. Okay, there are 5 different distributions that need to be explained as part of getting you to truly understand the comparison distribution for the between groups t-test. So I'll try to go over this slowly, explain this in a good bit of detail. It is described in more detail in the textbook if you really want a very granular or fine-grained summary of the comparison distribution. In short, the comparison distribution, it is what we call a distribution of differences between means. Okay, so the comparison distribution is a t-distribution that is, okay, so it's flat compared to a normal distribution. The t-distribution, and it is a distribution of differences between means. To understand that, I'm gonna give you a whole bunch of ideas, but to understand that, realize here's the t equation. The t equation is going to be m1 minus m2 divided by s sub m. S sub m is the standard deviation of the distribution of differences between means. S sub m is our standard deviation for our comparison distribution. This is the t formula. Okay, and these are m's, not mu's. Those are actually m's. So mean 1 minus mean 2 divided by the standard deviation of our comparison distribution. Distribution of differences between means. This is based on 2 different distributions. Each of these, this is based on an n of 3. You're going to get a mean based on this sample, based on this n of 3. And this is based on an n of 2. So we have 2 different potential distributions of means. have distribution of means representing population 1, or mu sub m sub 1, and then we have distribution of means representing population 2, which is mu sub m sub 2. They will have different standard deviations from each other because they are based on different n's. And you remember, a distribution of means gets lower as your n gets higher. And since these distributions of means are based on samples that have different n's from one another, you're going to have different standard deviations for each of these distributions. And you will see that information from the variance, which is related to the standard deviation of both of these distributions, feeds into information about the variance of our comparison distribution, which feeds directly into information about the standard deviation of our comparison distribution. So we ultimately are going to use a distribution of differences between means, right? Because we're looking at a difference between means in our t-test. And that distribution of differences between means is created partly from the distributions of means that correspond to the different samples. And each distribution of means relates to a population distribution. So the distributions of means relate to population distributions. So this experimental drug distribution, we have some sample data, 98, 97, 99, corresponds to a theoretical distribution of the temperatures of everyone with coronavirus who takes the drug or who could potentially take the drug. And this population here of the control is theoretically based on all of the people with coronavirus who are not taking the experimental drug and what their temperature is after 3 days of treatment. In the control case, the treatment is placebo. So we have these population distributions. Distributions of means are created based on population distributions, and a distribution of differences between means is created based on the distributions of means representing both populations. That's kind of a long theoretical explanation of what a distribution of differences between means is. Let's get into the math of it. So this is going to be real similar to stuff we've done already. First, we're going to get information about the variability of scores for sample 1. So the first thing we're going to do is subtract out the mean from each individual score. The mean is 98. Okay, x1 minus m1, deviation score, 98 minus 98 is 0. 97 minus 98 is -1, 99 minus 8 is +1. Okay, so that's our deviation scores. x1 minus m1 squared, so this is our squared deviation scores. Here we have 0, 1, and 1. Okay, now, we're going to get sigma x1 minus m1 square, which is the sum of the squared deviation scores. This is math we've done throughout the semester, which is 1 plus 1, 2. Okay, next, we are going to get s square square sub 1 is our best estimate of the population level variance based on data from sample number 1. S square sub 1 equals sigma x1 minus m1 squared divided by n1 minus 1. Okay, so that's a standard thing that we do with our t-test, is when we're estimating our variance, instead of dividing by n, we're dividing by n minus 1, which has the effect of giving us a slightly increased number, which represents this idea that there's more variability at the population level than there would be typically at any sample level. So it's just a way to mathematically increase the answer. That is going to be 2 divided by 2. Look at that, kids. 1. So s squared sub 1 equals 1.
Thank you.
Okay, I'm going to hold off on things right there. And we're going to get something similar for our control data. But we're going to come back to that. Okay, for the control data, so that's s squared sub 1. I'm looking for s squared sub 2. Once I get s squared sub 2, we're going to start doing some calculations with s squared sub 1 and s squared sub 2 that will ultimately give us our standard deviation of our comparison distribution. But I'm holding off right now. We've got s squared sub 1. Let me move to get s squared sub 2. Same exact process. Okay, the mean is 100. X2 minus M2, 101 minus 100 is 1, 99 minus 100 is negative 1. I'm going to square those. X2 minus M2 square, 1 square is 1, negative 1 square is 1. And then sigma X2 minus M2 square is 1 plus 1 is 2. Don't you like easy numbers, kids? 2. Now, okay, so the sum of the squared deviation scores for sample 2 is 2, and s squared 2, which equals sigma x2 minus m2 squared divided by n2 minus 1. Okay, so again, you remember this is like the average of the sum squared deviation scores. Instead of dividing by n, we're dividing by n minus 1, which has the effect of pushing that up just a little bit to take bias into account, because samples have smaller amounts of variability than do populations they are drawn from. So s2 squared equals 2 divided by 1, which equals 2. So s squared sub 1 equals 1, s squared sub 2 equals 2. All right, here's the thing. Who remembers the concept of homogeneity of variance? The answer is you. And in case you need a little refresher, the concept of homogeneity of variance is the assumption that unless there's a compelling reason otherwise, we're going to assume that the population level variance and standard deviation, representing different populations for the same kind of variable, are equal to each other. So we have no prediction regarding a different pattern of variability of temperature for people who take the experimental drug versus people who take the control. And therefore, we're going to assume homogeneity of variance, which means that we're assuming that the population level variance for people who take the experimental drug in terms of their temperature equals the population level variance of the control group in terms of their temperature. Therefore, s squared sub 1, which equals 1, and s squared sub 2, which totally by chance equals 2, are both estimates of the same thing. They are both estimates of what we call the pooled population variance. Neither of them is perfect, they're not equal to each other, we're not sure which one is closer to the truth, but we have information from two different samples. So the next thing that we're going to do, let's see if I can make space for this here. We're next going to come up with something called S-square pooled. S-square pooled means your best mathematical estimate of the population level variance based on pooled information, information that is pooled from both samples. So that is why it's called S-square pooled. It's essentially a weighted average of the variance estimate for sample 1 and sample 2. Okay, the formula for S-square pooled is this. df1 over df total times s square sub 1 plus df2 divided by df total times s square sub 2. That is our formula for S square pooled. All it is, if you break down that formula, you're just weighting the different variance estimates based on sample size. Remember, degrees of freedom is just n minus 1. And total degrees of freedom, I'll put a little sidebar here, dft equals df1 plus df2. So we have degrees of freedom from sample 1, which is 3 minus 1, which is 2. We have degrees of freedom from sample 2, which is 2 minus 1, which is 1. And looking at the degrees of freedom relative to the total degrees of freedom is just a way of giving that estimate a certain weight. If degrees of freedom for one sample is higher than it is for the other sample, then the estimate of the population variance should be given more weight because it's based on more information. In short, this formula, S square pooled, df1, n minus 1 is 3, minus 1 is 2. Degrees of freedom total is 2 plus 1, which is 3. So, and again, because n1 equals 3, so degrees of freedom 1 equals 2. And n2 equals 2, so degrees of freedom 2 equals 1. And degrees of freedom total is simply df1 plus df2, which is 3. So that's where those numbers came from. So it's 2 over 3 divided or times 1, which is s squared sub 1, plus degrees of freedom 2, which is 1 over degrees of freedom total, which is 3, times s squared sub 2, which is 2. And so that equals 2/3 plus, it's just wild, 2/3.
Yeah.
Whoa. Doesn't always work out that way, kids. Which equals 4/3, which equals 1.33. So S square pooled, am I right about that? That's one of those easy math things that I think I should be 100% right at. S square pooled is 1.33. Our best estimate of the population level variance is 1.33. So I'm gonna erase all this information except hold on to 1.33. Dana, don't let me forget that.
I won't.
Okay, so S square pool equals 1.33. All right, kids, I'm gonna put a little sidebar right here, and I'm gonna keep it here. S pooled. S pooled is the square root of S square pooled. So S pooled is the square root of S square pooled, which is the square root of 1.33. which is 1.15. Okay, let me tell you, that's a little sidebar. That's something I'm putting in my back pocket right now. We will not need S pooled to figure out the standard deviation of our comparison distribution. However, we will need S pooled later when we compute effect size, because if you remember, effect size is based on estimates of variance that are independent of sample size, and S pooled is independent of sample size. S pooled conceptually is our mathematical best estimate of population level standard deviation in temperature across both populations. So S pooled, while it's not going to be used for our t-test, S pooled is conceptually meaningful, and we will use it for our Cohen's d, which is our index of effect size, in a little bit. I'm going to keep it in that box. Am I going to erase that box, kids? Nope. Dana's not going to let me erase the box. Okay, so S square pooled. You remember, our comparison distribution is a distribution of differences between means. Remember, we had 5 different kinds of distributions. We have our population distributions. We have our distributions of means that correspond to the population distributions. And then we have our distribution of differences between means. We're going to do everything at the level of variances instead of standard deviations all the way until we get to the very bottom. So S square pooled of 1.33 is our best estimate of the variances of these two distributions, which are the distributions representing the populations. How do we compute the variances for the distributions of means? Okay, so first we're going to get S square m sub 1, which equals S square pooled over n sub 1. And similarly, we're going to get S square m sub 2, which equals S square pooled divided by n sub 2. Those correspond, S square m sub 1 and S square m sub 2 correspond to the distribution of means variances for each of the relevant distributions of means. So you remember, these two distributions will feed into our comparison distribution, which is our distribution of differences between means. This is a distribution of means representing population 1. This is a distribution of means representing population 2. S square sub m sub 1 is the variance of this distribution, and S square m sub 2 is the variance of this distribution. And we need both of those to ultimately feed into our distribution of differences between means, which is our comparison distribution for our t-test. And we'll see that S square pooled is used as the numerator for both of these. So once we've computed S square pooled, that became the only relevant estimate of population level variance. It was based on information from both samples. It pooled the information together. It weighted things based on the different sample sizes. And now we're just dealing with S square pooled. And we're dividing, for each of these distribution of means variance estimates, we're dividing by the relevant n, which gives more weight to an estimate that is based on a higher n, which again is a theme throughout stats. So S square m sub 1 equals 1.33 divided by 3, which is 0.44. And S square m sub 2 equals 1.33 divided by n sub 2, which is 2, which is 0.67. Okay, so now we have our information about our variance estimates of our distributions of means. Both of those pieces of information in a cumulative fashion will give us information about the variance of our comparison distribution, which is the distribution of differences between means. So I'm gonna make a little space right here. So here's my comparison distribution, which is my distribution of differences between means. The variance of that is called S-squared diff. Oh, by the way, my t-test formula I put up a long time ago, S diff, not S sub m, is actually the denominator of that. I wouldn't worry too much about that, but realize it's S sub diff, not S sub m, and when we compute it, you'll see that we'll do that correctly. I apologize about that. Okay, the variance of our comparison distribution is S square sub diff, meaning the estimate of the variance of the distribution of differences between means, and it simply equals S square m sub 1 plus S square m sub 2, which is just a way of saying that it takes, in a cumulative fashion, both estimates of both distributions of means into account. So that simply is 0.44 plus 0.67, which equals 1.11. And then S sub diff, which is the standard deviation of the comparison distribution, is simply the square root of S square sub diff, which is the square root of 1.11, which is 1.05. So our standard deviation of our comparison distribution is 1.05. That was a lot of work to get to complete step number 2. But that is the completion of step number 2. That is the relevant information. It's the comparison distribution for our t-test. For any t-test, any t-distribution, the mean in t units is 0, and the standard deviation in this case is 1.05. Okay, I'm not going to erase that thing in the box. I'm going to erase some of this. Okay, let's see how this goes. Step number 3. Okay, step number 3 is going to be t-critical. For t-critical, I'm going to need to have given you alpha, which I haven't done yet, but let's put alpha at 0.05, which is pretty standard. And we can take a look in our book at our t-table, which we've looked at yesterday whenever you looked at this last, page 329. Here's our t-table. Okay, now, the first question is whether this is a one-tail test or a two-tail test. Remember, we're predicting that the experimental drug leads to an improvement in temperature or a lowering in temperature, meaning it is directional. So we have what we call a one-tail test because we're predicting a difference in a particular direction. Okay, in terms of degrees of freedom, we're going to use degrees of freedom total, which is based on degrees of freedom from sample 1 and from sample 2. Remember, we calculated that degrees of freedom total is actually 3. Okay, so it was 3 minus 1, which was 2, plus 2 minus 1, which is 1, which is 3. And our alpha is 0.05. So we're going to go over here, and you see this right here, 2.35. That is the answer, 2.35. Okay, so that is how we figure out the critical value. I'm going to draw, hopefully I can erase this stuff. Okay, I'm going to draw my comparison distribution, t distribution, and t critical equals 2.35. Okay. The next step, and if you've been sitting through these videos or through this class all semester long. You know the next step. Once we have our critical value, we're now going to get our obtained statistic. In this case, we're going to call it T obtained. And T obtained equals M1 minus M2 divided by S sub diff. Okay, which equals 98 minus 100 divided by 1.05. Okay, so that is looking like -2 divided by 1.05. And my calculator has that as -1.90. Okay, a couple of things. I'm looking and I realize that I made a teensy-tiny error, but we can fix it. The critical value is supposed to be negative. The reason the critical value is supposed to be negative, so -2.35, I'm going to put it over here. And again, I apologize for not catching that sooner, but remember it follows the research hypothesis. The research hypothesis is that mu1, the temperature for people in the experimental group, is lower than mu sub 2. And in that particular case, we're predicting that M1 should be lower than M2. So we're actually predicting a negative T. And since we're predicting a negative T, our T critical is on this side, on the negative side. Again, I apologize, I didn't catch that earlier. It's relevant at this particular moment. So this is the point at which it's important to catch it. T, or T obtained, is -1.90. So you remember, a T distribution has a mean of 0. The standard deviation of this particular T distribution is 1.05. And T obtained is right here at -1.90. Okay, I'm going to take my pink marker and demarcate my alpha region. Okay, if I were going to reject the null hypothesis, my obtained t-score would have to be in that alpha region. It would have to be more extreme than my t critical. It is not in the alpha region. It is close to the alpha region. If I were really doing this research, I would say to myself, darn, I probably didn't have enough statistical power. I probably should have rejected the null hypothesis. And you remember with statistical power, that kind of means you should increase the n. So if I were doing this research legitimately, I would probably redo the study with a much larger n and see if the findings actually came out. But here we have t obtained at -1.90. T critical at -2.35. The final thing, step number 5. Hope I'm not erasing too much stuff. Final thing, step number 5, is we're going to comment on the null hypothesis. And the answer is this: we fail to reject the null hypothesis. Okay, so when our T obtained is not as extreme as T critical, and when it is not in our alpha region or our rejection region, we fail to reject. Fail to reject means our data are inconclusive, so we don't know. It doesn't mean we're wrong. It means we don't have good evidence saying that we were probably right, is really the best that we can put it. A final thing that we can do, and it's the reason that I saved that box right there today, final thing that we can do is calculate the effect size. So with between groups t-test, effect size is based once again on something called Cohen's d, and it equals M1 minus M2 divided by S pooled. Remember, S pooled was not used in computing the standard deviation of the distribution of differences between means. It was not used for the t-test, but it is used now for effect size. Effect size estimates are independent of sample size, and that's the reason we're using S pooled here. That's the difference between the t-test and Cohen's d. The t-test uses S sub diff, which is totally based on sample size of two different samples. S pooled is independent of sample size. It's an estimate of the population level standard deviation separate from sample size. So this equals the absolute value of 98 minus 100 over 1.15. My calculator says that is 2 divided by 1.15. My calculator says that is 1.74. Remember, effect size doesn't care if it's positive or negative, which is why we use the absolute value. How big is your effect in an absolute sense? 1.74. Remember, based on standard effect size conventions, small is about 0.2, medium is about 0.5, large is about 0.8. 1.74 is essentially huge, so we had a really big effect size. The reason we didn't reject the null hypothesis was not because of the lack of a big effect size, it was rather a lack of a large enough sample size. So hopefully this topical example gives you a sense of how the between groups t-test can be used and is actually right now being used by scientists around the world to help address this kind of issue. Hopefully this shows you how applicable and relevant statistics are in your everyday life. This has been Stats with Glenn.